So the title of my talk is the following: Computer-Assisted Medical Decision in Angioplasty Vascular Intervention. I'm from Poznań University of Technology. I decided to prepare my talk according to the classical convention, and in this agenda I will maybe just underline that today I will mainly focus on my results and the application of my research. So what is this balloon angioplasty? This is kind of medical procedure which is conducted in the cases when the patient has arteriosclerosis. The arteriosclerosis is the disease of our cardiovascular system. Here you see the example of artery which is diseased. In the blood lumen there is some formation of a plaque, and this formation of a plaque limits or decreases the blood flow. And one of the way to overcome this reduction of the blood flow is to introduce the balloon in a place where the plaque is formed through the wrist axis or by the groin. Of course, this is done by the physicians during the intervention. The balloon is introduced on a catheter, and then when it reaches the plaque, the balloon is inflated, and then the balloon, by contact, squeezes the plaque. The next step of the intervention is to deflate the balloon, and then the balloon is removed from the body. So what is the motivation? Of course, we can find in the literature many facts about this, how important are those interventions, the treatment. And today I decided to present the data from the World Health Organization, which reported in 2018 that the two world top leading death causes in 2016 were related with cardiovascular disease. If we consider this in our region, I mean the European Union, then we can also find data of Eurostat, the European Statistical Office of EU, and the Eurostat reported that in European Union 38% of all deaths were caused by cardiovascular disease. Of course, this is quite a lot. So you see that those problems in our society related with cardiovascular disease, the problem is quite severe and important. If we look at it from different perspective, I mean the financial one, we can find the data reported by Reuters agency that in 2014 the worth of balloon angioplasty global market was about 1.8 billion United States dollars. So taking into consideration all of those facts, I decided to, let's say, put my brick to this problem or to this treatment somehow, and I stated the thesis that using numerical methods may allow us to get deeper insight into this mechanically based cardiovascular intervention in order to improve the safety and efficiency of the procedures. Of course, the area or the topic is quite broad. Therefore, I focus on three topics, which was the core of my thesis. The first topic was related with determination of material parameters of calcium deposits. Those are the tissues which are formed at some severe stage of arteriosclerosis. The second topic was related with prediction of a mechanical effect during the balloon angioplasty. And the third topic was related with the complication, with kind of complication which is sometimes reported by the physicians, the complication of the migration of the balloon. So sometimes before the balloon is fixed in the artery, it's migrating before the intervention. Okay, and in order to solve those problems or work with them, I had to prepare two, let's say, group of finite element method models. The first one was related with indentation test of calcium deposit. Those tissues were tested by Magdalena Kobielasz in Wrocław University of Technology in 2014, and I used her data as an input to my inverse problem solution. I had to build a computational model of the test, and in a quite classical approach of inverse problem, I determined the material parameters of those tissues. And the second group of the models were related with this balloon angioplasty, or quite similar intervention called intra-aortic balloon occlusion. I was also an observer of such interventions in a group of Professor Oshkinis in University of Medical Sciences, and based on those experience and quite recent or state-of-the-art literature, I was able to define the computational model for this procedure, which was a 3-layered artery with some spherical balloon. Of course, in those computation, I had to use a number of constitutive relations. The first two are related with biological materials. So the first one is the first material is thoracic aorta or common iliac artery. I use here the quite known in biomechanics computational constitutive model of Professor Holzapfel, Gasser, and Ogden, which has such form in strain energy density. This constitutive relation is anisotropic. The material has anisotropic properties due to the inclusion of collagen fibers. And the second model, quite important from point of view of my study, is the model. Is the material of calcium deposit. This one was proposed by me, however, according to the classical plasticity literature, and those 4 parameters shown here were the parameters which were determined in my study, okay, for this constitutive model. And the 4 materials which you see here were used to the balloon was made of those materials, so I I computed 4 cases of the balloons. So the nylon balloon, polyethylene terephthalate, PET, polyurethane, and silicone. And those were mainly hyperelastic relations. Okay, and now some of my results, a few examples. So those plots are the example of one solution of inverse problem when we consider this determination of material parameters or constants. On the left-hand side here, you see some values of material constant, Young modulus, yield stress, and some parameters of plasticity. And you see how in one solution of minimization, the values of those parameters are changed in iteration of the minimization algorithm. Okay. On the left-hand side here, you see the objective function, which is minimized through the iteration with its decomposition. So here is the total value of objective function and some decomposition of it, also shown for iterations. In order to improve the chance to find the solution which is optimal in a global way, I used several initial vectors of those materials, the unknown one, and compute and solve this minimization problem several times. I reached 7 numbers of vectors which were, let's say, locally optimal, and I selected the one with the lowest cost function. And the conclusion from this part of the study could be that, or there is a conclusion that the constitutive model with dedicated material constants with was determined, which take into consideration the permanent deformation of the tissues. Okay, and further results of my study. Here you see the plot of displacement of the balloon in points B and A in the artery, it's shown for 3 different stiffness of the balloon. In point E, you see the red curve, or the displacement in axial direction, and displacement in B are shown for horizontal direction here. And what is important here, if we compare the blue curve and the red one for particular balloon pressure, we see that there is some difference of 20%. It means that the deformation of the balloon would be more ellipsoidal one. But what is maybe more interesting here is the green, or are the green curves, which represents the technical specification of the balloon. So those are the data somehow released by the producer of the medical device. And this difference with the blue line here means that the producer somehow overestimates the diameter which his balloon would somehow show. Okay, so not including the artery stiffness gives meaningful overestimation of the balloon diameter, and this could be useful information for the physician to know that if he would pump this balloon in the artery, of course, the artery somehow would limit the balloon, and then its diameter would be lower, in fact, smaller. Okay, and further results. Here you see some plots which could be used to predict the behavior of the balloon during the intervention, while we have different stiffness of the balloon. So this plot could be used, for example, if the physician would like to obtain the, let's say, radial displacement of 2 millimeters. If he takes typical balloon, then he knows typical balloon means that the stiffness ratio is 1. He knows that the application of the balloon pressure should be like 4 atmosphere. Okay. So based on this plot, on those plots, the intervention prediction of deformation, balloon pressure, or required or diameter of the balloon may be obtained. Okay, and the further results are regarded with this commercially used balloon materials. I've selected 4, as already mentioned, nylon, PET, polyurethane, and silicone. And those results which you see here are related with or are showing contact pressure between the balloon and the artery, shown for different coordinate of the balloon. So the point B from previous scheme is for this coordinate 0. Okay, and what we can observe here is that the contact pressure for the nylon and PET balloons are higher than for softer balloons. So for polyurethane and silicone, the contact pressure are lower. Also the contact zones are larger for those 2 balloons. Okay, and this is also somehow repeated in the deformation fields of the results of deformation fields. So you see here that the contact zone, for example, for polyurethane is larger than in PET case. Okay, and now last plot from the results. This also regards to 4 commercially used balloon materials. Here you see the plot of migration resistance for different balloon pressures. This migration resistance is some kind, let's say, it's the magnitude which was computed by integrating the contact pressure for circumference of the balloon. Okay, so this value somehow can show us how much the balloon would resist to be moved through the, let's say, elevated blood pressure or other effects. And what is important to see here is that for compliant balloons, the softer one, those balloons tend to increase the migration resistance rapidly. So it means that this would be more desired behavior by the physician, because faster the balloon would somehow fix in the artery before the intervention. Okay, and all of those conclusions are now summarized here in those bullet list, and also some original achievements. I would like to present them at the end of my talk. Maybe what is worth to mention at this point that I implemented a constitutive relation for Gasser-Ogden-Holzapfel model with some extensions from the literature, and it was also verified in a few examples in Abacus. This is the second page of those original achievements from my thesis. And maybe at the end I would like to say that mainly I focused on computations and kind of, let's say, study which would be useful for the physicians and producer of medical devices, and that would be all. Thank you for your attention.